Prove Torricelli's theorem. Prove Torricelli's theorem. This is a tank containing liquid. This is a tank containing liquid. This is the free surface of liquid in the tank. Free surface of liquid in the tank. Free surface of liquid in the tank. Height of liquid in the tank is capital H. Height of liquid in the tank is capital H. O is the orifice or narrow hole on the wall of the tank, which is at a depth h from the free surface of liquid. The hole, narrow hole or orifice O is at depth h, small h, from the free surface of liquid. Liquid coming out through the orifice will describe this type of parabolic trajectory. Parabolic trajectory described by the liquid coming out through the orifice from the tank. And we can denote velocity of efflux. V is the velocity of efflux, that is the velocity with which liquid flows out of the orifice on the narrow hole. We can assume that the velocity of efflux at the free surface of liquid will be 0. That means liquid is at rest at the free surface of liquid. V0 means velocity of efflux at the free surface of liquid is 0. And atmospheric pressure acting on the free surface is P. Similarly, same atmospheric pressure P will act at the orifice O. P is also the pressure energy of liquid per unit volume. Let O be the orifice, that is a narrow hole. O be the orifice, that is a narrow hole. At a depth h below the free surface of liquid. Below the free surface of liquid in the tank. O be the orifice at a depth h below the free surface of liquid in the tank. The liquid in the tank flows out of the orifice O on the wall of the tank. The liquid in the tank flows out of the orifice O on the wall of the tank with a velocity v and describes a parabolic trajectory. Describes a parabolic trajectory before striking the ground. Describe the parabolic trajectory mid-air before striking the ground. P is the atmospheric pressure. P is the atmospheric pressure acting on the free surface of liquid. Atmospheric pressure acting on the free surface of liquid in the tank. And also P is also the pressure energy of liquid. P is also the pressure energy of the liquid per unit volume of the liquid. Per unit volume of the liquid at the free surface of liquid. It is assumed that same pressure energy per unit volume of liquid, same pressure energy per unit volume of liquid will act at the orifice O. That means P is the pressure energy per unit volume of liquid acting at the free surface of liquid. Similarly, P is also the pressure energy per unit volume of liquid, acting at the orifice O. We can denote the free surface of liquid as A, applying Bernoulli's theorem. Applying Bernoulli's theorem at the free surface of liquid, that is at the point A, and at the orifice O, we get P plus rho gh plus half rho U square is equal to P plus rho G H minus H plus half rho V square. The pressure energy, potential energy and kinetic energy per unit volume remains constant. P is the pressure energy per unit volume, rho G capital H is the potential energy per unit volume, and half rho U square is the kinetic energy per unit volume of liquid at the free surface. And at the orifice O, P is the pressure energy per unit volume, that is same pressure energy per unit volume X, and the orifice is at a height from ground, is at a height H minus H from ground. That's why potential energy per unit volume is rho G H minus H, and kinetic energy per unit volume of the liquid is half rho V square at the orifice O. Where the pressure energy, where the pressure energy, where the pressure energies per unit volume of liquid, per unit volume of liquid at the free surface of liquid, that is at the point O, at the point E, that means at the free surface of liquid in the tank, and at the orifice O, the orifice O are same, that is P, that is P, and the velocity, and the velocity of a flux, velocity of a flux at velocity of a flux of liquid at the free surface is zero, that is small u equal to 0 at the free surface of liquid. That is at the point A, u equal to 0 means at the free surface of liquid velocity u equal to 0, or comma p plus rho g capital H plus half rho into 0 equal to p plus rho g h minus rho g small h plus half rho v square, or comma 0 equal minus rho gh plus half rho v square, or comma half rho v square equal rho gh, or comma v square equal 2gh. Therefore v equal root over 2gh, v equal root over 2gh. This is the velocity of a flux through velocity of a flux of liquid, velocity of the flux of liquid through the orifice O, through the orifice O of the tank, through the orifice O of the tank, which is equal to the velocity v prime equal root over 2gh acquired by a body falling freely under gravity for a vertical distance, falling freely under gravity through the same vertical distance, gravity through the vertical distance small h, which is equal to the depth, which is equal to the depth small h of the orifice O below the free surface of liquid, below the free surface of liquid, below the free surface of liquid. Here in the diagram at the point A, the body was at rest, a body of mass small m was at rest, means u prime equals 0, and the body reaches to the point O and it acquires a velocity v prime. It acquires a velocity v prime using v square equal u square plus 2a dot h. We get v prime square equal u prime square plus 2gh, or comma v prime square equal 0 plus 2gh, or comma v prime equal root over 2g small h. V prime equal root over 2g small h. So v prime is equal to root over 2g small h, which is the velocity acquired by a body, velocity acquired by a body falling freely under gravity, falling freely under gravity. Hence Torricelli's theorem is proved. Torricelli's theorem is proved. V equal root over 2gh. V is the velocity of efflux of liquid. Velocity of efflux of liquid and root over 2gh is the velocity acquired by a body falling freely under gravity.